Hello, my name is Giacomo Antonio, and in this presentation I will talk to you about our new work, automated camera calibration via homography estimation with graph neural networks. The topic of camera calibration has been extensively studied for decades. It is the building block of most real-world computer vision applications, allowing us to transform pixel coordinates to real-world coordinates and vice versa. Traditional approaches rely on some assumptions, including but not limited to vanishing points detection, key points detection, predetermined object informations, or anchor images. These approaches fall short in the context of traffic cameras, where physical access to the cameras is often unfeasible, and environmental conditions can influence the accuracy of the calibration process. The method we propose in this work is based on two key ideas: leveraging the topological information of the intersection, and approaching the problem from a graph perspective. Our framework relies on semantically segmented synthetic images, which allows us to train our models on the topological structure of the intersection and to take into account environmental and traffic conditions via semantic segmentation. We generate thousands of synthetic images by sampling virtual camera parameters and using their homography to warp a semantically segmented bird's-eye view of an intersection. The generated images are randomly split in training, testing, and dictionary splits. We then construct a training and a testing graph, in which each image is considered a node. Both graphs share only a subset of nodes, the dictionary nodes. For simplicity, we will refer to input nodes as the training and testing nodes. The input nodes are connected to the top 20 most similar dictionary nodes. In the same way, the dictionary nodes are also connected to other dictionary nodes. As shown in the picture on the right side of the slide, a dictionary node connected to another dictionary node could be in the second hop of an input node. At training or testing time, we sample a batch of training or testing nodes from the respective graph. We will refer to these nodes as input nodes. For each input node, we randomly sample 10 of its dictionary nodes in the first or second hop. In the picture, you can see a reduced version of a mini batch with only 2 dictionary nodes per input node. Our proposed framework consists of 2 parts: an embedding generator component and an homography estimator component. The embedding generator learns to produce a representation of the input nodes and their respective neighborhood, which is then fed to a spatial transformer network to estimate the homographies. The embedding generator is trained individually at first, but after 20 epochs it is trained end-to-end along with the homography estimator. To generate the embeddings of the nodes, a lightweight CNN generates feature vectors for every node in the mini batch, including the dictionary nodes. We also construct a matrix representing all possible links between every node in the mini batch. We feed the feature vectors and the links matrix to a graph neural network model. We train the graph neural network to predict which links are true and which are not, assigning to each a score. The embeddings generated by the graph neural network of the dictionary nodes of the top 10 scoring links are batched together with the embeddings of the respective input node and fed to the homography estimator. Training the embedding generator component by itself at first allows the features extractor and the graph neural network to learn some useful information for the spatial transformer network, making the whole framework converge faster. The spatial transformer network estimates an homography for each input node based on their embeddings and the embeddings of their neighboring nodes. In order to generate the final homography, the estimated homography is multiplied with the homography of the dictionary node of the highest scoring link. The resulting homographies are used to warp the same bird's-eye view image used to generate the synthetic data, producing a warped image for each input node. These images are compared with the original image of the respective input nodes via a pixel-based loss function. We use the topological loss that we introduced in a previous work. This loss function was designed to leverage the similarities in the topological features of two images. The complete framework is trained end-to-end. We compared our framework with two similar previous approaches. Both works leverage semantically segmented synthetic images, using a Siamese network to find the single best match for the input image in a set of images called dictionary. The matched image is used as an anchor for the input image, and a spatial transformer network learns to estimate the homography between the two. We experiment on 5 synthetic datasets obtained from 5 real-world intersections, plus the World Cup 2014 dataset, and 5 real-world cameras that we placed in intersection number 3. Each experiment is carried out 5 times, each time with different training, testing, and dictionary splits. We also experiment with 3 different graph neural network models, namely the standard graph convolutional network, the graph attention network, and its improved version. To evaluate the experiments, we use the intersection over union metric, as reported in the table. All 3 graph neural networks outperform previous approaches on all datasets, with the GATV2 implementation being clearly better than the others in most cases. It is interesting to see that our framework has approximately the same accuracy on all datasets, except for intersection number 4, which has a more complex topology. I refer you to our paper to see the difference between the intersections. For what concerns the experiments on the real-world cameras, we trained the model on the synthetic dataset of intersection number 3, in which the 5 cameras are placed. We repeat the experiment 5 times with different training and dictionary splits, and we report the average result. We show that our framework outperforms the previous state-of-the-art. The GATV2 implementation slightly outperforms the other graph neural networks also in this case. We observe a dip in the performance of our framework on the real-world cameras by up to 7% when compared to the experiments on the synthetic datasets of intersection number 3, where the cameras are placed. We conjecture that this is due to the quality of the segmented images that we obtained using DeepLab v3+. We show an example of these segmented images in figure C. In conclusion, in this paper we proposed a framework for automated camera calibration that outperforms previous state-of-the-art approaches. Our framework is also computationally more efficient than previous single anchor approaches because it does not require to compare each input image to each possible anchor. We also showed that using a dataset composed of semantically segmented synthetic images, structured like a graph, allows us to leverage graph neural networks and obtain an accurate and automated camera calibration. Furthermore, using segmented images allows us to account for environmental factors such as weather conditions, traffic, and the lighting of the scene at night. For further information about this work, I encourage you to check out our paper and get in touch with us via email. Thank you for watching this presentation, and goodbye.